Right, in this video, I'm going to go through the Edexcel AS paper. This is the 2019 paper, paper 1. I'll just do the first half and I will do the second half in a later video. Okay, so I'm starting off with the multiple choice. How many ions are present in 306 grams of aluminium oxide? Okay, so first of all, we need to work out the number of moles of aluminium oxide. So moles aluminium oxide, mass over MR. So that's 306 divided by 102 is the MR of aluminium oxide. So that gives us 3 moles. Okay. Now 1 mole of aluminium oxide contains 5 moles of ions. 2 aluminium ions and 3 oxygen ones. So 3 moles altogether is going to contain 15 moles of ions. 3 times 5. And so to work out the number of ions, we need to multiply that by the Avogadro constant. So it's going to be 15 multiplied by 6.02 times 10 to the 23. And that gives us an answer. It's D. It's 9.03 times 10 to the 24. Okay, next question. What is the electronic configuration of the sulfide ion S minus? So I've got the periodic table there. Here we've got sulfur. Okay, so we have got 1s is filled up, 2s is filled up, 2p is filled up, 3s is filled up, and then with sulfur we would have 3p4, 1, 2, 3, 4, but it's 2 minus, so we've got 2 extra electrons, so it's not 3p4, it's 3p6. Okay, so the answer there is D. Right, question about isotopes. What this is a GCSE question really, is it what's meant by isotopes? So it's nuclei with the same number of protons, different number of neutrons. Or you can say the same atomic number and different mass number, that's fine to say that. Right, so here we've got gallium as a relative atomic mass of that, and it only contains 2 isotopes. Okay. So a sample of gallium contains 69, and that's the abundance of that. So what we need to do is work out the mass number of the other isotopes. So what we're going to say is then that AR is equal to the sum of the abundance of each isotope multiplied by its mass. Okay, so here we've got 69.735 is equal to, right, we know that the abundance of 69 is 63.25, so that's going to be, we'll do it as a decimal, 0.6325 multiplied by 69. Okay, the other isotope, let's say that the other isotope is X, right? That's the mass of the other isotope. Now the abundance of that other isotope is going to be 100 minus 63.25, so that's 36.75%. So that's going to be plus 3675x. Okay, so solve that for x. Let's do that. So we get 69.735 is equal to, multiply that out, you get 43.6425 multiplied by 0.3675. Simplify that. So subtract 43.6425 from both sides of the equation, you get 26.925 is equal to 0.3675x. So x is equal to 26.925 over 0.3675. That is equal to 71 is the answer there. Okay. Right. Question now about group 2. So this is which of the following describes the trends in thermal stability of group 2 carbonates and nitrates? Right, so this is a straightforward factual recall, and the stability of both of them, they both increase as you go down the group. Okay, so starting off, we've got magnesium, calcium, strontium, barium. Barium carbonate and barium nitrate are the most stable of those two, so that A is the answer. Okay, describe with the aid of a labeled diagram how you compare the thermal stability of two group nitrates using simple equipment. I think that's what they're looking for, something pretty simple. So what I would do, I would get probably bubble the gas that is being produced. Now the gas, right, when you decompose a nitrate, how are we going to detect that? Well, let's say we've got magnesium nitrate. You get magnesium oxide, which is a solid, and you get 2 moles of NO2 gas, and that's brown. So that's very easy to see. And then you're also going to get O2. What I would do is I would just simply get a boiling tube, clamp it, put some solid in there, get a Bunsen, and heat and time how long it takes to see brown fumes. Okay, to see brown fumes. And once you've got brown fumes, you know it's thermally decomposing. Okay. Right. A safety precaution. Well, NO2 is poisonous, so you must do this in a fume cupboard. That is all you need to say, I think. Right. Which of the following describes the trends in stability in solubility in water of the group 2 hydroxides and sulfates? Right. Again, straightforward recall. As you go down the group, the sulfates become less soluble, and as you go up the group, the hydroxides become less soluble. So the answer there is the hydroxide, as you go down the group, the hydroxide solubility increases, and the sulfate solubility also, the sulfate solubility decreases. So you would want there, B is the correct one, isn't it? Hydroxides become more soluble, sulfates less soluble. Okay. Right, question about iron 2 salts. What's the percentage by mass of anhydrous iron 2 sulfate? Percentage by mass of iron in anhydrous to 3 significant figures. Okay, so the MR of that, if you work it out, is 151.9. The AR of iron, one iron atom was 55.8. So the percentage iron by mass is going to be 55.8 divided by 151.9 times 100. That gives 36.7. There is the answer there. Okay, describe a chemical test and the expected result to show that sulfate ions are present in a solution of iron 2 sulfate and water. Right. You should really add not just, well, you add barium chloride and it should be acidified, obviously not with sulfuric acid, but with hydrochloric acid or with nitric acid, and you'll get a white precipitate. If you've got any sulfate ions, you'll get a white precipitate of barium sulfate. Okay. So Mohs salt is another compound containing iron 2 ions. Okay, it has the formula, it's given there. So what is the molecular mass of that? Well, the NH4 is 14, so that's 2 times, so that's 14. Iron is 55.8. The sulfate, that weighs 96.1, the sulfate ion. And waters, I'll probably remember, are 18. So you're going to have 2 times 14 plus 55.8 plus 2 times 96 plus 6 times 18. That gives us 392. So the answer is A. A solid white water soluble compound was thought to be magnesium bromide. Okay. Student carried out tests to confirm the identity of both ions. A flame test was carried out for the cation. Okay. How would you carry out a flame test? Well, you get a piece of usually nichrome wire or platinum wire. Dip it in conch HCl to clean it. Heat it in the Bunsen flame, and then place it in some of the solid of interest. Place the wire in the solid of interest, and put it back in the Bunsen flame on a blue flame, and look out for the flame color. Right, explain the origin of flame test colors. Okay. Right, so what happens is the heat energy causes electrons to be promoted to a higher state, to a higher orbital, higher energy orbital. And then when the electrons return to the so-called ground state, to the orbital they should be in, when they return, you get the energy is released in the form of electromagnetic radiation. And that is what causes the color to be imparted to the Bunsen flame. The electrons going back to the ground state, releasing that energy as electromagnetic radiation. Right. Give a reason why the magnesium ion doesn't produce a flame color. Right now, they're really looking for something very general there. I think all you can say is that the energy emitted must not be in the visible part of the spectrum. Okay, so when the electrons fall back to the lower state, the energy emitted is not in the visible spectrum, so you can't see it. So there's no color there. Maybe in the UV part. Okay, give a reason why a lack of flame color is not a positive test for magnesium ions, because of course, like lots of things will not give a flame test, and so it's not only magnesium ions that won't give a flame test, all sorts of things don't. All right. Okay, give the formula of a reagent that would produce a cream-colored precipitate when added to aqueous solution of magnesium bromide. Okay, right. Cream-colored precipitate is due to the bromide ion forming insoluble AgBr. That's cream-colored. It's a test for a bromide ion. And so what you need to do, you need to add, and just say the formula. So you want acidified silver nitrate solution. Okay, so AgNO3 is the answer there. They ask for the formula. The identity of the anion may be confirmed by testing the solubility of the cream color precipitate in ammonia. Which pair of responses helps to confirm the identity of the ion? Right, now you probably remember that silver nitrate is soluble in dilute ammonia. You've got a bit of a trend. Silver bromide is only soluble in conch ammonia, and silver iodide is insoluble in both. So solubility in dilute is insoluble but soluble in concentrated. So B is the answer there. Yeah. Okay. 7, this question is about the reaction of magnesium with dilute hydrochloric acid. Okay, write an equation for the reaction of magnesium. Okay, that's pretty straightforward. So Mg plus HCl is going to give you magnesium chloride, MgCl2, because magnesium is a 2+ ion, of course, and you will get hydrogen gas as well. So we need to balance that, put a 2 there. Okay, the apparatus shown in the diagram can be used to collect the gas produced during the reaction of magnesium dilute hydrochloric acid. Okay, so we've got hydrochloric acid, and the hydrogen gas is going to come up here and into the bubble up here into the inverted gas jar. Right, the following procedure is used. So they set that up. Piece of magnesium ribbon was weighed, and they give you the mass there. Delivery tube and bung were removed from the test tube. The magnesium is added very quickly. All right. Okay, so you're going to lose a bit of gas there with that method. It's not a brilliant method. And when the reaction was complete, the final volume of gas recorded. Okay. Right. A measuring cylinder is used to measure the 10 centimeters cubed of dilute hydrochloric acid. The uncertainty for the measurement is 0.5. Calculate the percentage uncertainty. Well, it's going to be the uncertainty divided by the volume, which is 10, multiplied by 100, and that is going to give you an uncertainty of 5%. Okay, determine which reactant is in excess by calculating the number of moles of magnesium and the number of moles of hydrochloric acid. Okay, so here we are told the moles of magnesium, well, we're given the mass of magnesium, so moles Mg is equal to mass over Mr. So the mass of magnesium, in the question it says we had 0.12 grams. 24.3 is, well, I should say the AR of magnesium, really not the MR. And that gives us a number of moles, 4.94 times 10 to the minus 3. Okay, now we've got to do the moles of hydrochloric acid. We can do that from concentration times volume. Okay, so moles HCl is equal to conc times the volume. The concentration of hydrochloric acid was 0.2, it tells us, and the volume of acid we're adding is 10 centimeters cubed, so that's 10 over 1,000, which is equal to 2 times 10 to the minus 3. Okay, 1 mole of magnesium needs 2 moles of hydrochloric acid. So look, you've actually got way more magnesium there, you know, and can react with the acid. That amount of acid can only, that amount of magnesium can only react with divided by so divided by 2. Okay, so you would need 2 point, what's half of 4.94, 1 minute, 4.94. You would need actually 2.47 times 10 to the minus 3 moles of magnesium of hydrochloric acid. We haven't got that much. We've only got 2 times 10 to the minus 3. So the magnesium is in excess, minus 3 there. Calculate the maximum number of moles of gas that could be produced using your answers to A and B. Right. So the equation then, the magnesium is not in excess, is magnesium in excess. So the limiting reagent is the moles of HCl. Okay. So magnesium plus 2 HCl gives you magnesium chloride and just 1 mole of H2. How many moles of HCl have we got? Well, we worked that out. That's equal to 2 times 10 to the minus 3. So that means we are going to get half of that amount of gas, moles of H2, is going to be 1 times 10 to the minus 3 moles. Okay, under the conditions of the experiment, the temperature was 23 and the pressure was 98. So calculate the maximum volume of gas that could be produced. Okay, so we're going to have to use the ideal gas equation, which they give us there. Right, so we have to be careful with the units, of course, when we're using the ideal gas equation. I'm going to rearrange that. V is equal to nRT over P. Okay, so we need to be really careful there. We need to remember that the temperature is got to be in kelvins. So 23 degrees C, that is equal to 296 Kelvin. Okay, the number of moles, so let's do the number of moles of gas is 1 times 10 to the minus 3. The ideal gas constant, 8.31. The temperature, 296 Kelvin. The pressure, now they do give us in pascals, not kilopascals, so that's 98,000, that's the right unit. And the volume is, the unit volume is going to be meters cubed. Okay, so that, well, let's work that out. You get 2.51 times 10 to the minus 5. Right, too many multiplication signs there. Times 10 to the minus 5 meters cubed. Don't forget, there are a million centimeters cubed in 1 meter cubed, so we need to multiply that by a million. So the answer there is, multiply that number by a million is 25.1 centimeters cubed is our answer there. So it's the only difficulty there is remembering to use the correct units always. Right, 2 possible reasons why the volume of gas collected in the experiment was smaller than that collected in there. Right, now I think the main reason, the most obvious reason, is the way they collected that. But what they said they did, they said they just go back to this diagram here. The delivery tube and the bung, step 3, were removed from the test tube, and they put the magnesium in and very quickly put the bung back in. Well, if you do that, you are going to lose a tiny bit of hydrogen no matter how quick you are. So that would be the one reason. And the other reason I'd say would probably be because the magnesium might be impure. Most likely, so I'd say magnesium is impure, particularly magnesium might get a bit of magnesium oxide on the layer of it, on the surface of it. And of course, when that reacts with acid, you don't get hydrogen, you get water. So that would be why it's a little bit lower as well. Okay. Describe 2 changes to the procedure that would enable the volume of gas collected to be closer, okay, than to the calculated value. Well, first of all, I think you could remove the magnesium oxide layer by using some sandpaper, sanding the surface of the magnesium. That would be one. So and the second one, you need some kind of way of introducing the magnesium into the test tube, and then like sometimes you can do things like put it on a little bit of cotton and trap that. People do things, you can trap it in the bung, so you've got a piece of cotton trapped in the bung with the magnesium ribbon tied to it. Okay, and so all you have to do is just loosen the bung, and the cotton drops in to the acid at the bottom there, something like that. I don't think you have to be to great detail. You just have a way of dropping the magnesium without allowing any to escape. Okay, so this is about melting points. Okay, right. 3 marks. Explain the difference in the melting temperatures of magnesium oxide and potassium bromide. Okay, now look, they are both high. Magnesium oxide and potassium bromide are both ionic compounds. Magnesium is going to be right. Okay, so that magnesium oxide and potassium bromide. Okay, so magnesium oxide, that's 2+, and the oxide ion is 2-. Whereas potassium bromide, well, it's just a single charge on the potassium ion, a single charge on the Br minus ion. So you're going to get stronger electrostatic attractions in the magnesium oxide. I'd say, first of all, I'd say they're both ionic, yeah? And I would say stronger electrostatic attraction between the ions in magnesium oxide for two reasons, actually. One, they've got it's Mg2 plus, and the oxide ion is 2 minus, where in potassium bromide it's just a single charge. And then the second reason also is magnesium is quite a lot smaller than the potassium ion. Okay, so you think magnesium is in period 3, whereas potassium is in period 4. Also, oxygen, the oxide ion is going to be a lot smaller than the bromide ion because oxygen is in period 2 and bromine is in period 4. So there's more shells of electrons, going to be much bigger. So the charges on the ions and the sizes of the ions. Now, the smaller the ions are, the closer they can get together, the closer they can approach each other, and the stronger the electrostatic attraction. Right, explain why the electrical conductivity of solid potassium bromide is poor, but it is, well, of course, when it is a solid, the ions are in a fixed positions in an ionic lattice. They can't move. But when it's melted, the ions are free to move and carry the currents. Okay. Right, graphene, graphite, and diamond are all forms of solid carbon. Explain in terms of structure and bonding why graphene and graphite are good electrical conductors, but diamond is a poor electrical conductor. Okay, right. This is kind of a GCSE question, really, isn't it? Okay, graphite. Right. What you need to say is in graphite, the atoms are arranged. Carbon atoms are bonded to 3 others. Same with graphene. So there's a free electron, a delocalized electron, which can move under a voltage, and that's why they carry a current. Whereas if you look at diamond, carbon atoms are all forming 4 bonds. So all of those, all of the electrons are involved in bonding. So there's no delocalized electrons, so it can't conduct. Right, I'm not going to try and draw a diagram of graphite, I don't think. Right. Right, give 2 possible reasons why the density of iron is much greater than the density of graphite. Okay, you look at the right. So one, I would say that the atoms in iron, or the ions, actually they're going to be ions, so, okay, are more closely packed than they are in graphite. And the second reason, I would say that the atoms themselves in iron are heavier, more dense than the carbon atoms. So it's the density of the atoms themselves and also the way that they're packed. Okay. Right, the compressive strength is a measure of the energy required to break some of the bonds within a substance. Okay, deduce possible reasons why there are 2 widely different values for the compressive strength of graphite. Okay, so it's because graphite is arranged in layers, isn't it? Okay, you've got layers of carbon atoms like that, and so if you try and squash it that way, you can probably push the layers a bit closer together. So that's probably the lower lower compressive strength. Whereas if you're pushing it this way, in that direction, you can't push the layers together. All you can do is kind of crumple the layers, which is probably requires more pressure. It's because it's not the material is not the same in all directions, is it? It's made up of layers. Right, and I think that is as far as I'm going to go with that paper, and I will continue with the rest of that in the next video.